Mind if I just sit back here? I'll be quiet.
No, not at all. Yeah, definitely. We always have more than enough space. Yeah. Just a quick check-in. Where are we in lectures?
Busy with the monotonic increasing.
Okay, so they kind of told you a bit about the definition of sequences converging, and now they want to tell you if it's always increasing, it converges to the least upper bound. If it's always decreasing, it converges to the greatest lower bound. Okay, I think we're going to go back a step. I'm assuming everyone's going to be happy with that we're going to go back to like the definition of the limit today and just talk about it and do some examples. I think that's really important. The additional theorems that we prove are of course important too, but they're kind of meaningless until we feel really good about the first thing we did. Okay, so that's my kind of plan for today. I hope everyone's happy with that. Any other stuff apart from that that I should talk about either at the end of today or just in general? Yeah.
Can you do examples of convergence?
Using the definition, and yeah, that's exactly my plan for today. So the plan today, so maybe I'll just write it. So today, if you just want this for your notes, our plan today is definition of a sequence converging, and we're going to talk about why does this make sense? Some examples, of course, and like tips, tricks, techniques. Okay, so that's the idea for today. Anything else that? But I think this will probably take up most of the time, and it's a pretty good use of time. Okay, so the first thing is, maybe I'll talk a little louder, but let's take a look at a particular sequence. So it's a little bit fancy. What I have in my mind is this sequence, AN, where each term is going to be defined by 1 over n cosine n. Okay? And it looks a little bit fancier than some of the stuff we've done. We'll see that it's not too bad to work with. So what does this sequence do? It's important. You won't, for some really complicated sequences, we won't always be able to draw it easily without a use of a computer. But it's a good idea to see if you can draw it. If you can ever draw it, it's going to just help you a lot, right? So what is happening here? Okay, so if I just had the cosine n, we kind of maybe have an intuitive picture. We know what cosine does. It just kind of oscillates, it goes up and down. But it only happens at certain points, so I'm just going to see kind of points up and down, okay, if I just drew cosine. What does 1 over n do? We also have a picture of that in our head, like it starts out at 1 when n is 1, and then 1 over n just gets smaller, right, and it goes down to 0. So what happens when I multiply them together? I just have this thing that's kind of oscillating, and this thing is just making it smaller and smaller as we go along. So if I drew it really big, like if I put out like 1 over here, it's probably going to look something like this. It kind of goes down, comes here, goes here, goes here, goes here, You know, this isn't to scale or anything, but this is just to give you an idea of what's going on. And these would really be at discrete points, like, okay, I haven't drawn my points exactly equally, but this is the idea. So we have this idea that it's kind of converging. If I had to kind of connect the dots just very lightly, remember a sequence is always discrete, but it's kind of, okay? It looks kind of like that. If this was an x and it were a continuous function, it would look kind of like that. Okay. So, all right. So I'll just write something here. We intuitively know what AN is doing. This sequence, sorry, is doing. Okay, let's just put a box there. Okay. So we kind of know what it's doing. We're looking at it. It's a little bit hard to figure out. We'd have to use a computer to figure out each individual point, but nonetheless, we see its long-term behavior. We'd say that kind of as n gets large, I'm just going to roll the board up. As n gets, we'll say, big, whatever that means, then an gets closer to 0. 0. Okay. So we have a feeling that there's something like a limit going on. It's and it doesn't happen anywhere near the start. Whatever's going on here doesn't matter. It's kind of as we go to infinity, as we go farther along. And just to be really, really clear, I hope this was clear already, but when I'm plotting on this, I'm plotting the function an on the y-axis, and I'm plotting natural numbers on the x-axis. Okay? But it really is discrete points, because I have like kind of n equals 1, n equals 2, n equals 3, and so on. So we have a nice picture in our heads, and then the question is, how do we turn this into like math that we can use? And I don't know if anyone's still writing this. Can I erase it? Is it okay? Just showing you what we're doing today. Yeah. So we're going to talk about sequences, the definitions, and do some examples. But it's not too critical what's written here. Don't worry. All right, so then they give you this definition for all epsilon greater than 0. We agreed I would write my epsilons like that. For all epsilon greater than 0, there exists. Let's just be clear. When we're first learning this, as I said last time, I'm just gonna not. As you write these definitions more and more, you can start leaving out some parts. Like, you don't have to tell us every time that epsilon is a real number, but I'm going to write it just so that it's clear. We're not talking about a rational number. We're not talking about specifically an integer. Epsilon can be any positive real number. It can't be 0, and it can't be less than 0. Okay? So epsilon's a real number. For any positive real number, there exists some natural number, okay, such that, let me write it actually out just when we're first writing it, such that n greater than this implies that an is less than epsilon. Okay, and they're gonna write this down, and then they tell you, yep.
Sorry, is it a strict inequality that in
For this one,
great, yeah.
it actually doesn't matter.
Okay.
We can talk a little bit more about that just in 1 second. I think that's a really good question. It does not matter, and you will see both. So we'll talk about don't be scared about it when you see it, because it is confusing. Like, we make a big deal in math about like do everything exactly perfectly right, don't have little deviations, and then we have stuff like this and we can tell you, but don't worry, we'll talk about that. So they give you this whole long like sort of logic statement, and they say this is equivalent to the idea equivalent to the sequence AN converges to L, right? Okay. So our goal today is to match this up with that picture that we understood, and then be able to use it as well. We don't just want to understand it, we want to be able to use it. And it is actually a useful tool, although it's a little bit painful at first. So, all right. So let's see. Why does this say that the sequence is converging to L? Well, what I want to do is I really want to match up kind of this first part, or let's break it up in this way. But kind of this whole bit here, kind of there exists an n such that n greater than n. This part, which maybe I can call this like, this is like part 1 is like a single line or something like that. That matches up to this idea that we're just saying as n gets big. Okay. The whole purpose of that is just to describe this idea as n gets big. Okay. And then I don't have another color, but what I'm going to do is I'm going to use a little squiggly thing. We're going to say, if I do a little squiggly line under here, this part, and that technically, and this squiggly part, okay. So this is 1 here, and 2 is the squiggly line. This part is just saying an gets closer to 0, okay, for this particular sequence. But really we're saying for any limit L. So that's the purpose of these different parts. And we're going to talk about why do those parts actually say what I'm telling you that they say. We're saying that as n gets large, this number gets close to that number. And we have to talk about why does this mean that? Why does that inequality with the absolute value actually say that in a rigorous way? Okay, so what I think I'm going to do is I'm going to erase here. We'll maybe keep that picture. And I just want to show you something about how absolute value works. You may have seen this already, but if you have not, it's extremely critical that you see it. So I'll say let's pause and investigate the an minus L less than epsilon part. Okay? So we need to just talk about this. Okay? So what I want you to know, I'm not sure if you've seen it before. So last time we agreed that absolute value a minus b is the distance on the real line between A and B. Okay. So we agreed on that last time. Is anyone unhappy with that so far? Last time we were just saying if you draw the number line, it doesn't matter where you pick any 2 points, real numbers, A and B, this will give you the length of that. So it's always a positive number, it's just the length. I mean, it doesn't matter if they're positive or negative numbers or irrational or anything. I put in an A, I put in a B, I get the length. Okay? So here, and we'll rewrite that definition a little smaller somewhere and use it. Don't worry, it's not going away forever. Maybe you'd prefer it if it does go away forever. So the distance on the, but also we need, it's true that if absolute value of, say, A is less than C, this is equivalent to saying this: minus C is less than A is less than C. Okay? And we're going to use this all the time. Like, from now on throughout the course, we're going to use this all the time. So we need to know this. And so what we notice is, so notice that this object, when we say an minus L is less than epsilon in that definition, what we're really saying, that's equivalent to saying that minus epsilon is less than an minus L, which is less than epsilon. Sorry, I agreed I'd write my epsilons like this and then practice it. Okay? And that's really a minus sign right there. Okay? And that's equivalent. Remember, with any inequality, I can always just add a real number throughout, as long as I add it to all the parts of the inequality. So I can just add L everywhere, because I want to just learn about an. And so what I find out is that L minus epsilon is less than an, which is less than epsilon plus L. Okay? All right? So really what we're saying is, and I'm going to rewrite the definition kind of small up here because we're going to use it over and over. So we're saying that an converges to L is equivalent to saying that for all epsilon greater than 0, there exists a capital N in the natural numbers such that little n bigger than, for all the little n's bigger than the capital N, it implies that this inequality is true. Okay? Really, this last part, what it's saying is that you go on the number line, okay? You look at some point L, okay, this is just the real line, okay? And you go to this point L minus epsilon, and you go to this, you look at L plus epsilon, and what we're saying is all the ANs, so n greater than some capital N, all the ANs are somewhere in here. Okay? So I'm just going to say that again sort of from start to finish more clearly. This definition is telling us that we wanted to say that if we go large enough, the sequence is close to some number. And what I'm showing you is this little part here, it really is saying that. It's saying that you give me some number epsilon. Yeah, sorry, Gina.
Sorry, doesn't then that mean that all but finitely many ANs are there?
Exactly.
Oh.
That's exactly correct. That's actually a very good way of looking at it. We'll use that fact several times in some proofs that we're going to do. We're saying that I can go all the way, it could be a very large number, it could be 10 million, it could be 10 trillion, it could be 10, you know? But I pick some capital N, okay? You give me this epsilon, then I pick some capital N, there exists some capital N. I count up all the points in my sequence up to that capital N, I don't worry about them, they don't matter, and they're some finite thing and I don't care what they're doing. They might be close to L, they might not be. But after that, I'm going to require that if I draw this little diagram, I find L on the number line, I find L minus epsilon, and I find L plus epsilon, and I draw this kind of open interval. Remember, I'm really just drawing the open interval L minus epsilon, L plus epsilon. I need every single, the infinite list of the rest of the ANs. In other words, this is what we mean by little n being large. It needs for all of the things. We really can write for all here if we want. These ANs, and there are infinitely many of them, all need to be in this open interval. Okay? Yep.
So is this the epsilon neighborhood that Murray speaks about? Or something?
Yeah, we do use the word neighborhood to describe it. Yeah, this would be epsilon neighborhood. It is in your textbook. Depending on the course you get, you sometimes use that terminology, you sometimes don't. The advantage of using that terminology is it ties in with later areas of mathematics. So analysis is actually a broad thing. You have things like real analysis, where you study the real numbers. You have complex analysis, you study the complex numbers, similar techniques. And there are just broader ideas of analysis. And you start getting into ideas of where it just becomes much more useful to talk about a neighborhood. Because, for example, on the real line, we're talking about, we want to know about the concept of distance. We want these all to be close to L, okay? Now, we're doing real analysis, so we just have one dimension. We have a real line. But if we were doing something very abstract, we could have like 50 dimensions maybe. And then we're like, what do we mean by close then? We maybe want like some sort of abstract sphere or something like that. So that's where we start saying neighborhoods. But yes, this is the epsilon neighborhood idea. So we're saying finitely many of the terms in the sequence are doing something. We kind of don't care. And then as we get large, at some point, given an epsilon, infinitely many of them are close to L. And by close, we really mean that they are all inside, you could even write ANs are inside this open interval, okay? And we look at that, and we say, hey, how do I write that? What I really want to say is that AN is greater than L minus epsilon, and it's less than L plus epsilon, right? And that's equivalent to me just subtracting L from both sides, which is equivalent to this absolute value statement, okay? So have you seen this in lectures? Did we run through this in lectures? Okay, cool. And again, we will use that kind of trick often, okay? All right, so then now let's actually talk about some examples, because I think if we have a kind of a picture, also just to be clear, maybe I can draw on this image. It's going to get a bit messy because I already used yellow, but what we'd be saying if you wanted, so I drew it on the number line here. How this looks on this image is, of course, you give me an epsilon. We start out, you give me an epsilon, some positive real number. And on this image, I would draw something like that epsilon right there. I would draw kind of we believe that this is converging to 0. So here our L is equal to 0. We would draw L plus epsilon. L plus epsilon would be on the y-axis, okay? And L minus epsilon would be also on the y-axis like that. And we'd be saying that for large n, this sequence has to be between these bounds. Okay? Because remember, on the y-axis in this picture, we're plotting the sequence. We're plotting AN on the y-axis. So this is really messy. I'll try to draw it a little cleaner for some other examples that we do. But that's the idea. Remember, this open interval that we're pointing to, we're saying that all the ANs are inside that open interval. It's on the y-axis when you draw it this way. Okay? So we're really trying to say that if we go large, we can find this upper and lower bound and kind of squeeze everything between it. And since we can do it for all epsilons, we're kind of able to know that no matter how tightly I pull that, the ANs are all between those bounds, and so I feel that I really have found the limit of the sequence. Okay? All right, so let's do some examples. Just a question, how did the tutorial go? Were we able to do kind of the first few questions on the tutorial? Because I was thinking about talking about some of those, but if we really want to see them, then I'm really happy to do them, because that's great. If we don't want to see them, then maybe I shouldn't do those. Do them? Yeah, okay, cool. It was my plan to do them, but I didn't want to waste your time
I'm sorry, do you mean tutorial for this week or last week's?
Tutorial 4, which was, it started out saying suppose you have a sequence that converges to 4.
Okay.
Then can you show that these other things are true? Are we okay with seeing some of those examples? Okay. All right, so we're happy with this. I'm going to erase this as well. Yeah. And one more question, just so we kind of optimize the time we spend. Did we kind of see proofs in lectures of like 1 over n converges to 0? Did we perhaps see that? Yeah? Do we want to talk through that again? Okay, because that's where I was going to start. It's a good place to start. Okay, we probably don't need this as well. Actually, even this one. Let's start first here. All right, so let's do examples. Okay. So first things I just want to make some comments on strategies first. So so one of the first things you want to do is you kind of want to do rough work. And okay, actually, let me go back one step and we'll see this as this comes through. But I kind of pointed this out at the end last week, but I'll just say it again because it's really important. When we're actually carrying out this procedure, I can also read what this says in a different way. I can say that you give me any epsilon, I need to find this n such that something is true, such that a certain inequality is true. So really the hard part in doing this, or the constructive step, the thing that you need to achieve, is to find that n. Almost always the goal is to find that n. Not almost always, always. So we need to figure out what that n is so that I can say that for all the little n's that are bigger than that n, something is true, some inequality. And that kind of process is going to be repeated throughout the course. We'll have some other definitions that are kind of like this, but slightly different. And in those, we're going to similarly have like for any epsilon part, I need to find an actual object, like an actual number that makes something true, okay? So one of the first things you need to do when doing these problems is find the n, like try to kind of put it together. And my tip to you is don't try to write out the proof right from the start. If you can, do it. If you just know how to do it, you can see it, it's fine, or you've done that example before, perfect. But 9 times out of 10, your best bet is going to be do some rough work, try to figure out what inequalities and stuff are true involving the n, and then write it out carefully. Because it's kind of a nightmare to start these problems just in the formal language, writing out proofs, okay? So rough work, and what we mean by that is find n. Find n, check inequalities, play around, okay? And then 2, we write a formal proof. Okay? And then I'm just going to write here, really important, see Abbott. Okay. Start of chapter 2. So I think this book actually has done it quite well. If you read from the start of chapter 2, it's pretty short, but it explains it really well, I think. It shows you pictures, it tells you what's going on with the definitions, and it gives you a little checklist. It gives you like a kind of a 5-point thing. How do I solve a problem like this? First I do this, then I do this, then I do this, then I do this, and then finally I write the proof. I've kind of condensed it down here, but you'll see what I mean if you go read this. You'll always get more out of reading this than listening to me. But so I really want to point you that direction. Okay, so let's do an example. Okay, so we can look at something like this. An is equal to 1 over n. And we kind of believe, like in this case, we can kind of cheat a little. You might not always know what the limit is, but we kind of know that that an is 0, or we want to show that. Okay. We already have a good guess. Sometimes you have to go through a whole separate process of trying to figure out what the limit is before you can start proving what the limit is. Yeah.
And after you do these examples, because you also do an example where you have to find the limit if you can't guess
Sure.
it.
Yeah. Absolutely. Yeah. Just remind me if I forget, but I will try to do that definitely. I have one in mind, but it's a little bit different from this, but it's still a sequence that converges to something where you don't know the limit. But at the end of the day, look, there are also different types of questions you can be asked. You can be asked, like, someone can give you a question and say, find the limit. Okay, then obviously you have to find it. And then you might not have to write a proof, you just need to find the limit and maybe prove that it is the limit. And there are different ways that you can prove that something is the limit. You can use the formal definition. You can also use some of the stuff we're starting to talk about in class, where if you can show the sequence is increasing and you can show that that number is the least upper bound, then you've proven that it converges to that number. Because we have
What's that again? What did you say?
So we have a theorem, I'm not sure if we've done it yet or we're about to do it, but we have a theorem that says that if a sequence is increasing, always increasing, and it's bounded above, sorry, you need that too, it will converge to its least upper bound. Okay, so that's one way. If you find something and you can prove rigorously that it's the least upper bound and you prove that the sequence is increasing, in fact, it doesn't even have to be increasing the whole time, it just has to be increasing past a certain point to infinity. So if it's not increasing for the first two, in other words, if it looks suppose it looks like this. If the sequence looks like that, that's also fine. But anyway, I'm just giving you an example. Sometimes we use the formal definition, sometimes we'll do some more theorems that tell us other ways to prove that. But anyway, you can get a question that says, prove that this converges to that. Or you can get a question that says, prove that this converges. You might not need to find the limit, it just says, prove that it converges. So in that case, for example, in the one I just said, let's say you can show that the sequence is increasing, and you show that it's bounded above. You don't need to find the limit. You just know that it converges. Yeah. So it depends on what the question's asking, but in general, we're going to have to go through some process to find the limit a lot of the time. And then what we have to do with that after may vary. But okay. So let's look at this. So we're doing our rough work. All right. So rough work. So what's the inequality that we care about? It's this one. This is the thing. We're trying to somehow make that true for some values of n, okay? And we'll make that more precise as we go. So roughly, we're given, some positive real number. Okay. Epsilon, which is greater than 0, and we want to show that absolute value of 1 over n, sorry, why did I write that? Just an, right? Okay, sorry. So we want to show this, okay, is less than epsilon. Okay, now I see what I was thinking. And in our case, we're just going to plug in our values. So what is an? It's the sequence 1 over n. And what is the limit that we think it converges to? We think it's 0. Okay? And we need to show that this is less than epsilon. Okay? Okay. So at this point, you kind of write down what you know. And then you simplify a bit, okay? Makes it easier to see what you need to do. So really what we're trying to say is, if I just simplify that last line, it's equivalent to just saying that because 1 over n is positive, we're just looking at this inequality, okay? So far we've just looked at the thing we need to kind of investigate, this last part, and we just subbed in what we know, or what we think we know, okay? Now what does this kind of remind you of when you're looking at this? We've actually kind of seen something like this earlier in the course, and hopefully at this point, and if not, we'll remember it going forward, is this is like saying something about the Archimedean property, okay? We're talking about, remember the Archimedean property. Yeah, exactly. So the Archimedean property, if I had to say it in words, it's telling us that there are no real numbers that are bigger than all the natural numbers, and there are no 1 over n's there are no real numbers that are smaller than all the 1 over n's. Okay. So do I need to write that out, or are we kind of happy with that?
He's right there.
Write it out, yeah. So let's write just the word recall. That always helps. Just for like when you read it later, it's kind of structured. So recall, do I even know how to spell this? Archimedean. I'll spell it this way.
Yeah.
Is it E?
Yeah.
Thanks. Archimedean. EAN, thank you. For some reason I cannot remember it today. Archimedean property. That's good, you've been studying. Okay, and we say it in words. There are no real numbers bigger than all natural numbers. Okay? And that's actually equivalent. You don't really need a second thing, but we usually kind of tell it to you in two parts. That's completely equivalent to the idea that that kind of there does not exist, I'll write it here, any epsilon which is less than 1 over n for all n. And really epsilon is a positive real number here. Okay? Maybe I'll, again, just very specifically for your notes, say that epsilon is a real number. In this case, we're quite good about notation. If you ever see epsilons in pretty much any math course, where you're doing these inequalities and stuff, we always mean it's a real number and it's positive. Okay? But it's good to say epsilon greater than 0. So we're saying there's no sort of infinitesimally small real numbers that are somehow secretly smaller than all of the natural numbers when I put 1 over n. Okay? And that's completely equivalent to saying that there's no real numbers that are bigger than all the things. And how do I get that? I just reverse the inequality, right? I just divide and multiply. All right, so this looks a lot like that, right? That's the kind of pattern matching. But, yep.
So there are no real numbers bigger than all natural numbers.
Mm-hmm.
If you were to write it like in
Oh, you want me to write it? Sure.
form, would it be like for all x is an element of real numbers, there exists a y as an element of natural numbers such that y is greater than x?
Exactly, right? Because if you said, suppose that's not true, this is always the way we disentangle it, suppose that's not true, then there exists an x greater than y for all. You see, your for alls become there exists, and your there exists become for alls, and then it does exactly what we were hoping it would do. Yeah. Okay, so we're looking at this, and we're saying, okay, that looks a lot like when I just substituted into that definition my sequence and the limit that I think it converges to. I got this 1 over n less than epsilon, and that looks a lot like it has to do with the Archimedean property. So let's just kind of gather what we have so far. We want some n such that n for all n greater than n, 1 over n is less than epsilon. Okay, and we know there exists. We know that given epsilon, there exists a capital N such that 1 over n is less than epsilon. Okay, and just to be clear, this really is a capital N over here. It gets a little bit funny when I'm saying it in words, with little n's and big n's. Maybe I can put this up for you. So those are the two things we have. We wanted to find a capital N such that this is true, and we know from the Archimedean property there is this capital N that satisfies this, given that epsilon. Okay? And then, so we just kind of combine them because remember, we're learning that we're looking at the little n's that are bigger than the capital N, so this greater than this, you're going to see this all the time in the course, obviously means that 1 over little n is less than 1 over capital N. Okay? And, well, we know that 1 over capital N, there exists this capital N such that it's less than epsilon. Okay, so I just tacked that on the other side. Okay? And do we see that now, like, we wanted to say something about the 1 over the little n's, all the little n's, if they were bigger than some capital N is less than epsilon. And I've kind of very loosely put that together. I'm still going to write it out carefully as a whole proof so we can see that the logic works. But do we see that kind of this piece of the puzzle, okay, here, and this piece of the puzzle, and this piece of the puzzle are now fitting together? Yep.
By that no given that whole line, is it from the Archimedean?
This was exactly, yeah. And we'll still write this out carefully. Archimedean property. Okay, that was this line. An arrow. Okay. This was just the thing we needed to show. And this is the thing that we kind of constructively made. We got that. The Archimedean property guarantees us that this number exists. Okay? We don't have to feel uncomfortable that maybe we're making something up. And then we just put them together. And maybe now at this point it's useful to just write out the formal proof, yeah?
So do we always have to verify that that n exists?
So that's actually coming soon, but in general, I think, okay, general rule, I think you may have heard this in other math courses, is like, if something's proved in lectures, and perhaps, and I would check this with the lecturers, because I don't make the tests, so I don't know, but generally, if something's proved in lectures, you can use that. And so you can always reference it without like re-proving it, unless the question specifically asks you to do that. So let me kind of give you a specific example. If someone gives you 1 over n, like you open up your test and it says prove 1 over n converges to 0 using the formal definition of the limit. And you're like, in lectures, we showed, like, yeah, they're not going to be pleased about that, right? But if they say, and we're going to do an example like this in a moment, if they say, prove that this sequence, some other sequence, converges to something, and it becomes useful during the proof to just kind of bound, like find some inequality that is bounded, like this, you find some useful inequality that compares it to some capital N, at that point you'll be able to conclude that that capital N always exists. You can almost just say like, you can say, we'll see how it looks when we write out a proper example, but you'll be able to reuse this without spelling out all the steps. If you ever feel uncomfortable, just say like parentheses Archimedean property. Like, it's not that bad, but in general, it's pretty standard in math communities that like once you get to the step where you do a bunch of stuff and then you compare it to some 1 over capital N or 1 over little n that's related to an epsilon, you're done, because we all know that this now can always be found. Yeah.
I don't know, with the same question, can't you just say that since capital N is an element of natural number, there's always going to be another natural number which is always greater than it, that is from the Archimedean, the first property? Isn't that like sufficient?
In another problem, not this one, like if we were doing another problem and we got to that part. Yeah, I think if I'm understanding what you're saying, then yes. But remember that we need it to be true for all the little n's, so we always need to be careful to say that. It's not just that we can find some that will work. We have to always say like, there's always some list of little n's. But I think it'll become clear in the next example that we do. Because we're going to look at a different sequence, and we're going to show that that sequence is just kind of related, almost like a squeeze theorem type idea, that it's like always less than 1 over n. And so we're kind of done. But yeah, I think we're going to have to go through it by examples. But I would just say, here's my tip to you is check in with the lecturers. To what extent are we allowed to use stuff from lectures and stuff from tutorials without reproving it? Generally, the rule is you can use anything, as long as you just say like proved in lectures or something. But just check with them, especially about the tutorials, because some lecturers are fine with you using anything from lectures in an exam or in a test without reproving it, but they might not accept the tutorials, whereas other lecturers will say anything done in a lecture or a tutorial is allowed without reproving. Okay? But in this case, saying proved in lectures and saying Archimedean property are like the same amount of writing, so, but yeah, I take your point. Okay, so let's write it out formally. I think it's useful to do that now. We have some pieces of the puzzle. It may, for me, it's really comfortable. I'm like, because I've done this a million times, I'm like, oh, okay, we're done now. But it's really important to write it out formally and make sure that you're happy with the logic of everything that's going on. And then we'll do a slightly more complicated example. Also remember, anytime you're writing a test or an exam and you're not sure about something, just put your hand up. You're allowed to ask as many questions as you want. Like, the lecturer or the tutor or something can always say, sorry, I can't tell you the answer to that, that's too specific, but in general, it's really good to ask questions. So if you're writing your exam and you're like, do I need to prove this? Just put your hand up. And the lecturer will come over and you say, do I need to do this? And they're like, yeah, please do that, or like, no, don't. That always will make you feel better. All right. So that's a formal proof. Of let me write it this way: an equals 1 over n converges to 0. Okay. Suppose we are given epsilon greater than 0. Okay? By the Archimedean property, okay, there exists a capital N in the natural numbers such that it is less than epsilon. Okay? Right, and then at this point we just say, so, for all little n greater than capital N, we have 1 over little n minus 0 equals 1 over n, which is less than 1 over capital N, which is less than epsilon. And that's just like you're done at that point. That's really a minus sign in there.
So what do you mean graphically by this?
Sorry?
Like
Graphically.
graphically?
Yeah, we can draw that, definitely. Maybe I'll draw it right here. Okay. So let's say I plot 1 over n, all right? And I plot it, and it's going down, kind of like this. Getting closer, it never gets to 0, but it gets close, and it goes on. So this is little numbers n, all the natural numbers on the x-axis, and this is, well, we can just put 1 over n here, okay? And what this says is we kind of play this game. You pick an epsilon, anyone. Let's say you pick epsilon equals like 0.5 or something, or 0.1 or 0.01 or something like that. So you pick your epsilon, So this will be epsilon, okay? And what we're saying is there has to exist a point, capital N, okay? Now where is my capital N in this picture? Remember the natural numbers are going along here. The capital N is talking about these subscripts, the terms in the sequence. The capital N is some term in the sequence. It's a capital N. So this could be capital N, say here. So there exists some capital N there, and you can almost visualize it as a vertical line if you want to. And what we're saying is, and this term right here would be a capital N, okay, subscript capital N. Okay, so there exists some point in the sequence where for all the terms past it, all those terms have to be between 0 plus epsilon and 0 minus epsilon. So they're kind of, if I draw this line, and actually in this case, because all the terms are positive, we don't have to really worry about minus epsilon. But we want all these terms here, as we go to infinity, between these two bounds. Again, the picture ends up getting a bit messy, so I'll have to think a little bit about how to draw these pictures better, but hopefully that kind of makes sense. Okay, so really this is your capital N. I always think of it as a vertical line. Yeah?
Sorry, isn't those bounds like...
So if we're looking at, so remember we agreed that the that this an minus L part meant an needs to be between L plus epsilon and L minus epsilon. But in this case, L is 0. So that's L plus epsilon, L minus epsilon. Okay, and then we're happily in there. We pick another epsilon, we pick a smaller one. The bounds are in more. They're closing in, and then that capital N has to exist somewhere there, somewhere further along, such that all of the further terms, all infinite rest of the terms of the sequence have to be between those bounds.
So Jonathan, technically the dot just before the N should actually be outside, right?
This one.
No, the one before.
Yeah, that's correct. Actually, it doesn't matter. So maybe it's even better if I just leave it like that, just to emphasize that it actually doesn't matter. It just has to be true for all of them going past here.
At least, like, oh, okay.
At least. So it could be true that there's some before. And the reason, that's why I like the 1 over n cosine n, which we're going to do in a moment, by the way. We're going to prove that. We could have early terms, so maybe don't write this down because we're going to do an example in a moment that makes this clear. But I could move this. I could have some sequence where that's like right there, and we don't want to care about that. We want our definition to have nothing to do with these early terms. We don't mind if the sequence is somewhere close to some number at some point. It's really about for all points after a certain stage, yeah. So let's put that back up there. Okay. Are we happy with this kind of conclusion in the end? It's kind of like overdoing it a bit, but like it's really nice, I think, to write out super carefully exactly what we're doing on the first few examples. Do you also see that if I had to try write this out right from the start, unless I've done something like this before, it's going to be pretty hard. Like writing this all out in sentences and like constructing it as I'm going is going to be pretty hard. More or less can't ever do that unless it's a very easy example that you've seen before. Look, if you can, then do it, definitely. But really, I strongly recommend you want to go do rough work, go in the back of your book if you're doing your exam or something like that, and work out what's going on with these inequalities, work out what your arguments are, do it roughly, very roughly, and then try write out what's going on. And these kind of chains save you time. You know, it's like, here's the thing that we all agree we need to study. What is it equal to? Yes, this is true, and that's the final result I needed. I needed this to be less than that, and now we're done. Okay? All right, so let's go on to another example. Unless there are any more questions on this particular one. Nope? Okay. So the next one we're going to do is just this. is 1 over n squared plus n. Okay? And we'll just observe, like, again, we suspect an equals 1 over n squared plus n goes to 0. Okay? Why? Because I just imagine if the denominator is getting really big, the numerator isn't complicated. If it were complicated, I might have to make a further argument to study it, like if there were some numbers up here. But just because it's 1 over some number, and that number is getting really big, the overall thing is getting very small. Everything here is positive. So we're kind of believing that this is going to go down to 0. Okay? Okay, so we got to do our rough work. All right. And what are we studying? We want to study an inequality that kind of looks like this. It's an minus L less than epsilon. And in this case, what we're really looking at is 1 over n squared plus n minus 0 less than epsilon. Okay, so again, we're looking at something like this. Just subbing in at first, subbing into our definition. And we just simplify. In this case, simplifying is just an easy step. It doesn't require us to do much. We just are looking actually at this object. Okay. Yep.
Is 1 over n bigger than that?
Yeah, it is.
Can't you use that?
Exactly. Yeah, no, exactly. Yes, we can use that. That's exactly what we're going to do, and this goes back to the earlier questions. So almost everything you're going to be doing in analysis is using some kind of really abstract properties to learn some things, and then taking complicated things and seeing how can I compare them either to my abstract properties, my axioms or something like that, or how can I compare them to things I already know. And this is why we have to understand the proof of 1 over n, because we're going to compare lots of things to 1 over n. This is exactly right. So what we're going to say, we need to kind of mess with this, and we're going to say notice, and we're going to use these kind of tricks all the time. And I think I'll write it out in words. 1 over n squared plus n is less than 1 over n. Okay? And let's just write y. Well, the fastest way to actually do this, like you can sit and kind of do the inequality and compare and stuff, but the way you're going to have much more complicated things than this that you want to use the thing I'm about to write. Anytime you have positive numbers in the denominator, this number is going to be bigger than that number, right? If I just have a positive number and I add another positive number, it's bigger, okay? A bigger denominator means a smaller number. That's actually fast enough reasoning for us to go. We just want to feel confident in that. Now, if these can possibly be negative, we need to be a lot more careful, okay? So whenever you see minus signs and stuff floating around, you need to just pause and see what other kind of tricks we can use. But if I just have 2 positive numbers in the denominator, I can always throw one of them away, throw one away. I could throw away that one too. I throw one away and I get that. So we'll say 2 positive numbers added are always greater than 1 of the numbers and then so ... Do I need to write more here, or are we kind of happy? So ... denominators, I'm just going to kind of write that. Is anyone unhappy with that? Because I don't mind writing more, but we're kind of cool. So again, I'm saying if I have two positive numbers, I add them together, the result of adding them is always going to be bigger than one of those two numbers. So if I have them in denominator, you get the opposite inequality. This is bigger than that, so 1 over this is less than 1 over that. Okay? And we know from the previous proof that we can always compare this to some 1 over capital N, to some epsilon. So at this point, you wouldn't really write any more in your rough work. You would hopefully want to jump into writing your formal proof now. Okay? You have the argument you need. You needed to play around with inequalities to find something that's going to work. And so now we're going to go straight to our formal proof. Okay. And so we can just say, formal proof. You could just write proof when you're doing this, but I'm just kind of emphasizing the distinction between rough work and your formal proof. So it'd be fine to just write proof. So given...
In a test, do they give marks for the rough work as well? Or is it just the formal proof that counts?
Good question. I think that historically, when so I've marked a few tests and exams over the last few years, and I get given a memo, so I don't really decide, but I think historically I'd say that you do get marks for like reasoning that looks like it's right. So there's also other interesting things where like, maybe this is a sort of a different point, but like, if I can see that someone like compared the right objects and like got all together all the pieces of the puzzle right, and then you're just writing out your formal proof and you accidentally wrote like a there exists or for all or something, you might just get full marks minus something. You might like go up to a number and then minus, there'd be some penalty, right? Whereas, you know, I don't know how, sometimes the memos are set out in a way where it's like, yeah, you get points per piece of the puzzle. So they know that there are like sort of 3 pieces of the puzzle to do this problem. And if you get 2 of them in your rough work, then you got them. It's fine. It doesn't matter if we didn't see it. Even if you didn't have time to write the final thing, as long as I see it there, then it's cool. But, you know, the course is slightly different this year than it was last year. I imagine that that's still going to be exactly the same. That's pretty standard across lots of different courses. Okay, so given epsilon greater than 0, and here this is going back to our earlier question. You could say by the Archimedean property, but it would be sufficient for me at this point where you say, we know there exists a capital N such that, but we need to know why we know, but we would say there exists a capital N such that, maybe I'll write it up carefully, such that and maybe we'll hear for all n greater than that capital N, we start here, we know that 1 over capital N is less than epsilon, okay? We know that bigger little n's are always less, this 1 over little n is always less than 1 over capital N. And then this point, you can just write this, okay? I've never seen a test or an exam where you needed to like prove this step. If you know that this is true and you write this down, at this point to us, we hope that you know that this is true. We've talked about how you reason it out probably the quickest possible way, but this is fine. There is a sort of a subtle thing where it's like, how do you know, say you have a slightly more complicated question, how do you know how much effort you have to put into proving whatever you want to prove is less than something else when you're writing it out here? I would say that probably the point is if you're using a technique that has a name, it doesn't hurt to tell us what that is. You can have a little arrow. If you want to save time, you do this and you put a little arrow and you can say because because the numbers in the denominator are positive. So I think actually for the purpose of this, let's just add this to your notes. Because you could just write you could even write this. This is fine. You could write that. Or you could write a little sentence, because sum of two positive numbers, or you could just say because the numbers in the denominator are positive. That would just communicate to me that you kind of like thought about it for a second and you know why it's true. Yeah?
What if you use the same understanding for all small n greater than big N? You will have 1 over small n less than 1 over big N.
Yeah. Again, I would say that would be like, let's say you get your test and it says prove 1 over n converges to 0. And you want to do that step. Again, I think it's just like enough for me if you just say, because little n greater than big N, 1 over little n less than 1 over big N. And the reasoning behind this is it's not random. It may feel a little bit random, but it's really like if you use something that we've kind of said is just an axiom and we've proved it and it's in the course, then it's not surprising to us when you use it, and like we don't need a lot of extra justification. But if you're ever unsure, just give us a little signpost. And if you're ever unsure, put your hand up and say, do I need to do more here, or can I just move on to the next question? Kind of in this case, for that kind of thing, like for us, you imagine like the professor is marking it. He's looking at it, he's like, yeah, I know, I know how inequalities work, right? But I understand that there's a little bit of confusion where like, there could be something more complicated. And to him or to her, like it's like kind of obvious, but they need you to say it because they know you're learning it for the first time. And also there are some students who go on the test and just just write things and so, but anyway.
Jonathan, just on this proof, or just proving these, like the convergence theorem in general, I know with Murray, he told us that you should say, because it's basically given any epsilon, right?
Mm-hmm.
That would follow. So do
Yes.
we also have to like be very specific, be like, given any arbitrary epsilon greater than 0, we know that will happen. Because it's technically saying that whenever you give me an epsilon, I can
Exactly.
give you an n that holds for.
Exactly, it's a very good point. So we do have a for all right there, absolutely. And you do what makes the most sense to you.
Okay.
If it sticks in your mind, the way that your sentences flow out. Like if you want it to come out and you just want to write, this,
Okay.
that's perfect, okay? And if that makes you feel like, hey, I don't have any kind of lack of surety that someone's going to look at this. Maybe I made a little mistake. I know how this works, but I don't know how it works when I put in some sort of thing. Do the thing that works the best for you that you're certain is correct, okay? Do that. There is some flexibility in it. Where, because you see sometimes I write suppose, sometimes I write given, sometimes I write for all. The ones where you're going to get in trouble is this one. And yeah, because that's just literally not true. I mean, like, this is true. There does exist an epsilon, but this is not proving the statement that we need to prove. This literally has nothing to do with this. This tells me nothing about that. That tells me, okay, that tells me something about this. But, so that's the situation. So when I was first doing this course, I erred on the side of using the logic symbols, but then you have to feel confident with them, and you have to, because those you can't really go wrong with. If you write for all, it means for all. If you say like, suppose it could be true that, now are you saying suppose always, or you get what I'm saying. So do what works for you, but like check with tutors, check with professor that it's exactly right. I've thought about whether I should pick a convention and just show it to you always in the same way, but I think it's actually useful to see that these different things still mean the same thing, because you'll open a textbook, you'll open online notes, and you'll go, what's going on there? But really, do you see that when I say given or I say suppose, it captures the same idea? Because it's true for this epsilon, and because we put no restrictions on that epsilon except for it being greater than 0, we have now done it for all the epsilons. Okay, and that's actually built into the we know. We know that this procedure can be carried out for the epsilon. But okay, so we go with given, we go with for all of these are fine. All right, let's see, we got about 20 minutes, so let's see if we can do 2 more examples, maybe 3. Any other questions on this?
Just while you're raising that, Jonathan, is it possible for next week Monday, obviously, according according to the discretion of everyone else, since that's like test week, that we make it slightly longer.
Sure.
If
Yeah, that's not a problem for me. Depends how long you want. I think staying later is fine for me, and it's fine in terms of
maybe
the
it's like
venue
30
booking.
minutes more. So.
But I think the only issue is if you want earlier, which is probably more convenient for all of you because you don't want to like stay late because of dinner or something. But then I don't know how the venue booking works. But I can ask Billy about that. She is pretty on the ball about investigating all the admin stuff, so I can ask her. What day is your test next week? I'm actually Wednesday. Yeah, I mean, in principle, I don't really mind. I could do an extra hour if you want. But we discussed, the only thing is the admin side of it. What, is it better to be earlier, is it better to be later, and about the venue? But okay. All right, so next example. Let's say, well, let's quickly do this one. We started out talking about this. Okay. And again, sorry, I mean, I do owe you one where we don't know the limit, but again, we kind of suspect. We suspect that AN goes to 0. Okay. And we'll do a rough work. Okay. Sorry, I always use so much more. Okay, our rough work. And again, we're investigating this object, 1 over n cos n minus 0, and we need to show that this is less than any epsilon that we find. We can always find a way to make this for all those n's that are bigger than some capital N, less than some epsilon that we're given. Okay, any ideas what we can do now? Okay, so we simplify, of course, we always do that. Simplify. This time, this is not always positive, so we can't just take away the absolute values. We've been doing that up until now, but this really can be negative. So we just have this. Okay. You don't have to write the word simplify, by the way. That's normally not written. I'm just saying that because I feel like it kind of gives you a structure.
Can't you, since cos n is always between -1 and 1, that 1 over n cos n is less than or equal to 1 over n, and then use that again?
Exactly. That's exactly right. That's perfect. So again, we're going to try to compare to something we know. We know some certain properties of this, we know some properties of this, and so we know, and again, this is the kind of thing, you don't need to prove this. You don't need to prove that cos n is between -1 and 1. So again, there's a little bit of discomfort of like, what do I have to prove, what do I have to not to prove? But certainly, I mean, this is a fact we've been using all through like MAM 1000, so again, if you're really, really unsure, just ask, but we're going to use that over and over again, you don't need to prove it. Okay, so we know that absolute value, well, you can say it this way. Again, you wouldn't need to even write out these steps, but I just want to show you like a really sort of full logical way of looking at it. So we know that this is true, okay? And we've agreed that that's equivalent to saying that the absolute value of cos n is less than 1, right? Just from our discussion at the beginning of today. So altogether, we have that like, and again, I'm going to spell out the steps. I wouldn't write out all these steps if I were you. The most important step is, in fact, if if you were writing a formal proof in an exam, it would be enough to just write absolute value of this is less than absolute value of 1 over n, which is less than epsilon. There exists an n such that that's true. But I'm going to write it out a little bit carefully here. So this is equal to 1 over n cos n, which is less than or equal to mod 1 over n equals 1 over n, and we know that we can go. So
With the 1 over n cos n, isn't it by the triangle inequality that is less than or equal to?
this.
Like.
Oh, you wanted to do, remember that's for sums? So it would be 1 over n plus cos n would be less
so
than or equal
plus,
to,
okay.
yeah. When they're multiplied together, remember absolute value of a product is the product of the
Same
absolute
thing.
values. So that's why I'm glad I read out the step. If you're doing this in exam, you could really jump from here to here if you know what's going on. But I just wanted to write out the step because we're going to use that a lot. Remember, it's always true no matter, and again, don't have any worries about yeah?
But my question is for the use of the inequalities.
Which
at
one?
The,
Here?
Yeah, there and at the top.
And here? Yep.
Can we, is it
Sorry.
anything equal to or? So it's
Sorry about that.
Thank you.
Yeah. That's what we say safely. In fact, I think that you can possibly prove that it's strictly less than. I'll have to think about that a little bit. The reason for that would be, remember, you need kind of multiples of pi, or pi over 2, and that's irrational, and these are all net. Anyway, but we don't need it. Yeah.
Since for this all together part, we literally went from 1 over n is less than epsilon. Won't we have to prove that part?
So this is still my rough work. This is still my rough working. But yes, like I see what you're saying. We just kind of jump to this. This is just me sort of roughly writing on. This is how I'm thinking about it when I haven't like written my proof yet. Yeah. So now we just write the proof quickly. I think you all know kind of the way it's going to go. So, formal proof. So, now I'll just use a different thing each time, just so that we see all the examples of things that are acceptable. We will say that there exists a capital N such that n greater than n implies 1 over n less than epsilon. Okay, so we're going to jump to that step. Okay, do you see how I'm sort of each time leaving out a little bit more? Because it's not really the focus of this question. When you get this question, we're not really focused on can you go back and prove something about 1 over n? What we want to know is about this. And then here you would just write, we know that cos n is less than or equal to 1. Absolute value of cos n is less than or equal to 1. Okay. If you're not sure, if you're sort of like, man, do I need to work this out? Is there a left-hand side? You could go through that thing we did, where we said, remember, minus 1 is less than or equal to cos n is less than or equal to 1, and that leads you to this, okay? So I would say, or I would just say, absolute value of 1 over n, cos n, is less than or equal to 1 over n, which is less than or equal to epsilon. And that would be, and sorry, This was supposed to be an implies. Please correct that. That's quite important. We're not saying capital N is equal to this. We're saying this implies this. N bigger than that implies that. Okay. So do you see how I left out a couple of steps? But I have a robust proof, and we all agree that this has all the pieces we need. So this would be sort of an example of a totally sufficient answer to this kind of problem, because it's a slightly more advanced problem, so clearly we're trying to test that slightly more advanced part, and we're not so focused on, like, do you know this? We believe you that you know this. Again, if you're unsure, ask. And if the question says, use the Archimedean property to show that this is true, this whole thing, then you better do that other step, right? The part where you really show that this is less than 1 over n, and you say by the Archimedean property, which is less than epsilon. Okay? All right. Let's see. 10 minutes? Okay. So let's do another example. Any more questions on this one? All right. Let's do another example. I think now we can move to something from the tutorial.
Can we do an example where we don't know the limit?
Where we don't know the limit.
Yeah.
I have one in mind, but it's quite different from this. So I can show it to you, but the thing is, I think it will be better suited to next week, or we can chat directly after this, if you're okay with that. Just because the reason for that is, when you don't know the limit, I don't have one in mind off the top of my head where we're still going to kind of go through these arguments, but we're going to kind of like figure out what the limit is. But usually what happens in a case like that is you're given some sort of like weird looking sequence, and then they say like, find the limit and show that it converts, like find the limit of this, and prove it, And a lot of times, like I say, one that I have in mind is like you start finding upper bounds, and then you figure out what the least upper bound is, and you show that it's increasing, and then you say, okay, that's the limit. And that's quite a different spirit to like these examples. I don't have one in mind where you would kind of like derive what the limit is from this process, but there are things like that. So maybe I can add it as an announcement on Gula, or we can chat about that one I do have in mind afterwards. Is that okay? Okay. But we'll have a slightly different.
If we do have time, can we also do an example where the limit is not 0? So when we
Exactly. That's what we're going to do in the next one. So don't worry about that. A simple one I could give you is like, suppose I just added 1 to that sequence. That would be the most simple kind of thing. And so my new sequence is really 1 over n. So I'll just write it quickly. We could do, I'm not going to write this all out, but we could do 1 over n cos n plus 1, or plus 17 pi. Okay? Just some number. And we kind of suspect that this is going to 0. This would be a case where you might not know what the limit is. You might first look at this and be like, what the heck? But you kind of suspect, you kind of work it out that this is going to go to 0. And so if this is going to 0, then the limit's probably that. Okay? And so what you'll do is you'll write 1 over n cos n plus 17 pi, and then you'll write minus, I suspect that if I subtract 17 pi, I'm going to be able to bound this by epsilon. I don't really need that bracket. And we'll find out that it does work. So that would be like the most simple example. I could reverse engineer it in like an annoying way. I could put an n there, and then I could like make this like that, And then maybe you look at this and you're like, what the heck is that? Right? It looks terrible. Okay. What if I do this? I can add like a squared up there just to really mess with stuff, Can put a squared here and put like, So now it looks like a totally different problem, right? Okay. But at the end of the day, what are you going to do? Well, first you're going to simplify this, and you're going to see immediately, okay, well that looks a lot more like something I know. Okay. So I don't know if that counts as an example where you don't know the limit, because you don't. Like, you look at this, you don't know the limit. I don't know the limit. And then we play with it, and we're like, oh, okay, that cancels, so this is just some number, and then I kind of know what 1 over n squared times this is going to do. But when I say I know that, it's more like I've worked it out before, right? I know problems that are similar to that, okay? So that, in a sense, even when I tell you 1 over n cos n, we now feel really confident that we know the limit for that. But how did we do that? We had an idea, and then we proved it. Okay, we actually showed that we could do this procedure. Yeah. Okay, but let's see one where the limit's not 0 in detail. That's a little bit different in spirit from what we've been doing so far. Well, it's the same in spirit, but it requires a little bit more work. Okay. So. I'm going to actually just jump over the tutorial. And so we're going to do the first question, and we can actually, if we go quick, we can do the second question too, but let's see. We may not have enough time for that. So this is going to be TUT 4, if you just want this for your notes, TUT 4, question 1. And I think there was several parts, so question 1A. Okay, and I'll just write out briefly what they say. You are given a sequence AN which converges to 4. Okay. Now prove using the definition. Prove that, and they give you a bunch of different stuff to prove, but like say the first one they give you in part A is the limit as k goes to infinity of 3ak minus, and I think it was 2, equals to 10. Okay? So now this is slightly more complicated, right? We're going to run through similar steps. Okay.
Is that supposed to be AK tends to 4?
Well, so this is, and actually I noticed this, but I do it on purpose. So we need to feel confident that I can use different indices as long as we kind of agree that the same thing's happening. Perhaps I'm being a bit reckless there, but maybe I can start out here and do this if you want to change it. The reason I say that is you'll see sequences with lots of different subscripts, and we should feel fine about it always, but maybe within the same problem I should use the same subscripts. I think perhaps that kind of might indicate that I'm, unless I write out explicitly what I'm doing, it might indicate that I'm using different subsequences or something. So I think that's a fair comment. Okay, so, well, okay, so this is an example where the limit's not 0. Although we do know what the limit is. So we can, again, kind of follow our strategy. So this is our rough work. Okay. And we know we just need to look at this thing. So this is the object that I want to show has limit 10. So I'm just going to write 3ak minus 2. Okay. If you want to, you can put brackets around to kind of emphasize this is some sequence. And we want to investigate that minus 10. That's the limit. Okay. This is the object we want to study. And now we just simplify. Okay. So this is equivalent to looking at something that looks like this, 3ak minus 12 less than epsilon. Okay? And maybe you saw this in the tutorial, like maybe someone told you you worked it on your own already. But what do we do next? Yeah, so we have a common factor of 3. And really what actually is happening, we could really write down, so maybe I'll give you a guide about how I would think about it if I really didn't know what to do already. So that's what I'm studying. What I know, again, this is not a formal proof, this is just my rough work. I know that because there's something they've told me specifically about this problem. They've told me that the sequence converges to 4, so that I know, and I haven't kind of like put together all the puzzle pieces, but I know I'm able to work with something that looks like this. Okay? I have that already. I have that. That's what I'm thinking. I would just write this on my piece of paper. Note, I have this. So how can I make this look like that? Because I have this and I need that. Okay, so I pull out the factor of 3, right? That's kind of the logic of how I would go through it if I didn't know what to do yet. And so let's actually write that. So I would say this is equivalent. Maybe this is bad to do. Sorry.